So now we're going to go on and we're going to talk about electrons and the periodic table. Starting with valence electrons. We have not defined valence electrons very well. We have talked about it a little bit. The valence electrons are electrons in the outermost shell, the outermost energy level. And when we talk about the alkali metals, we have one valence electron. The number is, there's one. And if we were to write this with electron configuration and we use N as our first quantum number, because you'll remember that N, it means energy level. So if we're talking about lithium, it would be 2s1 would be the very last electron that goes on lithium. If we were talking about sodium, it would be 3s1. If we were talking about potassium, it would be 4s1. So this is the electron configuration for the outer shell. All right. The alkaline earth metals also have the same number of outer shell electrons, valence electrons. These all end in s2. So beryllium is 2s2, magnesium is 3s2, and calcium is 4s2. We'll go on to boron. Boron has 3 outer shell electrons. This is ns2, np1. So if we're talking about boron, it would be 2s2, 2p1. If we're talking about aluminum, it would be 3s2, 3p1. That would be the outermost shell. Carbon is going to have 4, ns2, np2. Nitrogen is going to have 5, ns2, np3. Now notice what I did here, how I spread those electrons out. What's the rule when Hund puts electrons to bed? We don't double up until we have to. So if we think of each of these sides of this circle as an orbital or an orbital type, these are the S ones, here's P1, here's P2, and here's P3, or PX, PY, PZ. We can kind of imagine that. That's why I'm drawing them the way I am. Okay, oxygen's going to have 6 outer shell electrons. It's going to have ns2, np4. So it'll have 3 electrons plus 1 that's doubled up. So 2 unpaired and 2 that are paired. For the halogen family, we have now 7 outer shell electrons. 1, 2, 3, 4, 5, 6, 7. ns2, np5. And then the noble gases, let's see if I can move that over, and I know how I can. Oops, I don't know what I just did there. Sorry about that. And of course it goes away. So noble gases have 8 outer shell electrons, except for helium. Helium only has 2, but it's a full shell, so that's important. ns2, np6. Okay, 2 outer shell electrons, 3, 4, 5, 6, 7, 8. Now, the noble gas electrons are called noble gases because they don't interact with anybody. Just like the nobility back in the day did not marry down. Jasmine couldn't marry Aladdin because he was a prince. He was not a prince. He was a commoner. It was a big deal when Prince Charles in England back in the 70s married Princess Diana. I guess it was 81. Married Princess Diana. It was a huge deal because she was a commoner. She wasn't born of royal birth. Most of the time they marry each other and it gets messy. So, noble gases have full outer shells. That's what atoms want to do. They all want to have a full outer shell, and we call that a happy atom. So if we look at an alkali metal here, An alkali metal has one electron in his outer shell. If he lost that one electron, his layer below him would be full, and he would be happy. So what alkali metals want to do is they want to lose one electron, and that'll make them happy. The alkaline earth metals, want to lose 2 electrons to get happy. The boron will lose 3 electrons to get happy. The carbon will either lose 4 or they will gain 4 to get happy. Nitrogen will gain 3 because he's got 5 in his outer shell. If he adds 3 more, he'll have a full outer shell. And it's easier, he could lose 5. But it'd be easier just to gain 3 than lose 5. Oxygen will gain 2, halogens will gain 1, and the noble gases don't have to do anything because they're already happy. If alkali metals lose an electron, they become more positive. So even though you think losing should be negative, because, losing is negative, think about it as giving electrons away. Giving is good, giving is positive. It becomes a positive 1. Everybody in this first family has a +1 charge. Everybody in the second family has a +2 charge. In the third family, a +3. The fourth family is either plus or minus 4. The fifth family is a -3. The sixth family is a -2. The seventh family is a -1. And once again, our noble gases are happy. Okay, that is the key to everything in chemistry, is that the way those electrons fill into the shells and then the way they can give their electrons away or share their electrons. That is what causes all chemical reactions. Chemical reactions occur with the electrons. The nucleus has nothing to do with chemical reactions, other than the fact that the number of protons determines how many electrons it's going to have, because in a neutral substance they want to be equal. Nuclear reactions take place inside the nucleus, so it's very, very small. Regular chemical reactions take place on the outside in that electron shell, so it's much bigger than the nucleus. Okay? Nuclear reactions release a tremendous amount of heat because you're breaking those bonds. But with the chemical reactions, you may actually take in heat during a reaction. Just depends on where their energy levels are as they go. All right. So that is our happy atom chart. Now, this is important, and I want you to hang on to this. And I'm going to pull up the next picture, so hang on. Actually, I don't need to pull up another one because I can put one more row on here. Okay? These are going to be what we call dot diagrams. For your 5th row, we're going to use X as just a generic. One outer shell electron, we're going to put 1 dot on him. Okay, if there's 2 outer shell electrons, we'll put 2 dots. We'll put them side by side because that represents our s orbital. Does it have to be on the right side? No, it could be anywhere. For our boron family, we'll put 3 dots on. For our carbon family, we'll put 4 dots on, 1 on one side and 1 on the opposite side from our 2. Again, it doesn't really matter where they are with relationship to each other because this is totally not accurate, but we don't know what it really looks like. For our nitrogen family, we'll have 5 outer shell electrons. For our oxygen family, we now have 1 doubled up. For our halogen family, we now have 2 doubled up. And finally, our noble gas family, everybody has 2. So they're happy. Dot diagrams are going to become very, very useful as we start drawing covalent compounds, which will be after the next test, so end of November into December. But we need to be aware of how to do it now.